A typical person accesses a large amount of digital data every day, and so do companies and organizations. Most of these data are transmitted by optical communication systems, which link up cities, countries, and continents. We are using optical signals, light signals, to transmit the data because light travels so fast that we can move enormous amounts of data within very short timeframes. They offer significantly higher data rates than other types of communication systems. In this video, we will explain the essential roles played by semiconductor devices in optical communication systems. In optical communication, the data is encoded in light pulses to be sent from the transmitter to the receiver. The light pulses travel along specially designed cables called optical fibers. Light can be described as a wave and a particle, a photon. A wave is described by its wavelength, which corresponds to different colors for visible lights. And each photon has a certain energy. The wavelength is inversely proportional to the photon's energy. Optical communication systems mainly operate at three wavelengths: 850, 1310, and 1550 nanometers to minimize signal losses. The choice of the system's wavelength determines the semiconductor devices used in the transmitter and the receiver. The transmitter is a light source, such as a semiconductor laser diode or a LED. They convert electrical digital signals into light pulses. Let's use the LED for now. When an electrical current is applied to the LED, we supply plenty of electrons to the conduction band and holes to the valence band. When there are many electrons in the conduction band and many holes in the valence band, there is a good chance that an electron will drop from the higher energy conduction band to the lower energy valence band, recombining with a hole. This is a recombination process. Often, the energy difference is made up by a photon. If there are lots of these recombinations taking place, then there are many photons being emitted and can add up to a useful level of light. It is easy to see that increasing the electrical current supplied to the LED can increase the LED's light output, but it is also important to minimize losing the emitted photons through internal absorption inside the LED. Otherwise, we would end up with some inefficient LEDs with large electrical power consumption. As light travels through the kilometer's length of optical fiber, it gradually becomes weaker. For long optical communication links, the light pulses from the LEDs are just not powerful enough, so lasers are used instead. Just like for LEDs, supplying lasers with electrical current allows lasers to produce light. However, lasers utilize a semiconductor phenomena called internal optical amplification, which occurs when very high electrical current is pumped into a tiny laser. A single emitted photon in a laser can kickstart more recombination processes, producing yet more photons. Semiconductor lasers also have optical cavities, further enhancing the internal optical amplification process. All these lead to lasers producing higher light output and being much more efficient in converting electrical energy into light output compared to LEDs. At the other end of the fiber, the receiver's end, the light pulses are converted back into electrical signals by semiconductor optical detectors. If the incident photon has more energy than the semiconductor bandgap, it will be absorbed. The photon's energy will then be transferred to the electron, so the electron can go up to the conduction band and produce an electrical current. We call it photocurrent. Of course, the energy exchange process is not perfect, so some of the incident photons will be lost without generating electrical signals. PIN photodiodes are the most commonly used optical detectors in optical communication. It is simply made based on a PN diode, but with an additional intrinsic region in between. The I region absorbs most of the light because it has very few free electrons and holes. The photon-generated electron and hole will drift by the reverse electric field to conduct the current. In this case, the optical signal is converted back into an electrical signal. To achieve very fast data rate, the photodetectors need to respond quickly to changes in light intensity. Besides, the photodetectors must be sensitive to ensure the attenuated light signals can be detected after a long distance. More sensitive photodetectors, avalanche photodiode, APD, also widely used in optical communication. The structure of an APD can be the same as PIN diode, but APD has internal gain due to the avalanche process. By adjusting the applied voltage, the electrons and holes in a relatively high electric field will gain enough energy to impact ionize with lattice atoms. This ionization produces secondary carriers, leading to a chain reaction, generating more electrical charges and amplifying the photocurrent. The optical properties of semiconductor devices are the crucial enabler for high-speed optical communication systems over short and long distances. Without these systems and the various technologies that depend on them, our daily lives would have been very different.